Hi guys, continuing on with the previous video, I want to do some examples with you about work. Just to recap, work is force over displacement times cosine of theta. There's two ways I want you to think about this really. There's intuitively what's going on, and then mathematically. So mathematically, I mean like this definition is going to come out positive or negative, but intuitively I want you to ask yourself, like thinking in terms of the LOL, is energy being added to the system or taken away, or is it staying the same? I also want to say, let's see. Okay, the way I'm going to run this video, I will present the problem, wait like 10 seconds. I ask you to pause the video, think for it yourself, and then I'll go over it. So that's the flow. So for this one, this is the initial velocity, that's the final velocity, the force is to the right, and the displacement is to the right. So what do you think? Intuitively, is energy being added or removed, or is it the same? And mathematically, what is the sign of cosine of theta going to be? Okay, hopefully you paused the video and tried it yourself. I'm going to make this blue. So on the left, intuitively, like the LOL, this thing is speeding up. You have EK, and then there's like more EK because the velocity is getting bigger. Mathematically, you have force to the right and displacement to the right. So the angle between them is going to be 0, and cosine of 0 is 1. Intuitively, mathematically. All right, try this one. Again, think about it intuitively, mathematically, pause the video, give it a try. Okay, hopefully you paused the video and gave it a try. So intuitively, again, the LOL, it's the same. EK and K increases. EK increases. I don't know that. It's speeding up. Mathematically, we have force and the displacement, and the angle between them is this. Cosine of, let's say, 45 degrees is still positive. So basically, there's some component of the force acting in the direction of motion, causing this thing to speed up. So both of these things agree. The work here is positive. Energy is being added. Here, cosine of theta is still positive. All right, what about the next one? Again, think about it intuitively, mathematically. Pause the video, give it a try. Okay, hopefully you tried it out. So this one, the LOL, it's moving at some speed, but it's moving at the same speed. So that's EK. So intuitively, no energy is being added or removed. Mathematically, theta is equal to 90. And cosine of 90, hopefully you know your trig, cosine of 90 is 0. So mathematically, the equation works out to 0. Another way that you can look at this is if you can think back to our unit on uniform circular motion. If I have an object moving in a circle, let's say it's over here, and then it's over here, and then it's over here. Whoops. No. I just hit Control Z and that messed things up. So let me erase that. Draw this a little bit more tangential. So the velocity is tangential at each point. And if you can remember, in what direction does the force point? Let me draw that in purple. The force, the thing that causes the thing to move in a circle, is towards the center. So purple was the force, and then red was the velocity. What does this have to do with work? Well, here you have an example of the velocity and the force being perpendicular, just like in this case. The force and the velocity at any moment are perpendicular. And what we saw in uniform circular motion was that the speed was constant. What the force was doing was just changing the direction. And so that's another way to see, like, oh, the speed is not going to be changing. Energy isn't being added or removed. It's not showing up as kinetic or anything else. So here the work done is 0. both definitions, both approaches agree, as they should always agree. All right, what about this one? You see the force, the angle, displacement. Intuitively, mathematically, think about it. Pause the video, try it. Okay, hopefully you tried it. So here, I'm really just zooming in on the velocity vectors. So it starts off at a certain speed and it starts to slow down. So I have a certain amount of kinetic, and by the end of it, I have less kinetic. Therefore, energy is leaving the system as work. I should have made that clear in the other ones. Here, there is no work, but here, work is being done. I should have showed it on the diagram. Better late than never. Okay, so here, energy is leaving the system. That's what I'm trying to show on the LOL. And then mathematically, when theta is between 90 and 180, cosine of theta is going to come out to a negative number. So just the graph of cosine, this is from 0 to 90. This is from 90 to 180, 180 to 270, 270 to 0. So this is the graph of cosine. So when it's in this, so this, sorry, this is 90. This is 180. On a graph of cosine of theta. So when it's between 90 and 180, which is what you have over here, that will come out negative. So the work done in this case is negative, energy is leaving. Mathematically, work done is negative. Last example, try it out. Okay, hopefully you tried it out. Very similar to the last one. I start off with a certain amount of kinetic, and I'm ending up with less kinetic because the initial velocity is greater than the final velocity if this thing is slowing down. So something you can kind of do is not a hard and fast rule, but if you're seeing the kinetic energy decrease, that is maybe a sign that energy is being taken away. It's leaving, usually because of some kind of frictional effect. You know, if I'm stopping something, so it's coming at me, I stop it, that's me slowing it down. The force and displacement are opposite. That would be like energy leaving that object. So that's what's happening over here. Work is negative, and then mathematically, cosine of 180 is equal to -1. Okay. So hopefully those examples were helpful. It might be good practice to come back to this video and try this practice again and see if you can get it all right. See you around.